we are having Julian Sahasrabudhe, who will tell us about the singularity probability of the random symmetric matrix.
Okay, thanks, Peter. I'd like to talk to you today about a sort of basic topic in random matrix theory. Although, like, perhaps on the face of it, it doesn't seem like something that's linked to spectral gaps, we'll see actually that it is connected certainly to the problem of understanding gaps in the spectrum. It's like sort of one of the key things to overcome. So I will touch on that, but also hopefully, even if you're unfamiliar with the subject, hopefully give you some appreciation for what's going on in the mathematics here. So I don't exactly know the kind of backgrounds you guys have, so I'm very happy for questions and to sort of adjust relative to so everyone gets a big out of this talk. Okay, so I'll mostly be talking about work here joint with Marcelo Campos, Matthew Jensen, and Marcus Michelin. But I might, depending on how we're doing, touch on some other work as well. So we've worked quite a bit together. Who are these people? So Marcelo Campos is a brilliant and just recently hired at IMPA in Rio de Janeiro. And I've worked quite a bit with him. He was in Cambridge as a Trinity GRF just before. Matt Jensen is in King's College, London. And Marcus Michelin actually just moved to Northwestern. Okay, so let's get with the basic object of the board. So I'm primarily interested in symmetric random matrices. And for me, most of the time, I could just imagine the matrix being a plus minus one matrix drawn uniformly among all such plus minus one matrices. I can do different distributions and all this kind of thing, but really this is already most of the difficulty. Just random, symmetric, plus minus one matrix, drawn uniformly at random. Okay, so we let Mn be drawn uniformly at random among all symmetric n by n matrices with all entries in plus minus 1, with entries. And so if you could change this distribution, you could weight it differently, whatever, but really already the most natural thing is the hardest thing. For the purpose of this talk, anyway. And the question, really the main question that I'd like to discuss, but I'll sort of try to situate it for everyone. But really the main question for us will be, what is the probability that this matrix is singular? That's it. So, what is the probability that this determinant is here? So what do I put here? And of course, I mean roughly, what is this probability? Asymptotically, what is this probability? So get some sort of feeling for what goes into this business, or what this number should be. Let me note a natural lower bound for this number. So sort of a very natural way for this matrix to become singular is if I have two rows, or equivalently, two columns that are equal or equal up to sign. So this quantity of interest here is always lower bounded by the probability two rows or two calls equal up to sign. And now this is actually a quantity that's fairly easy to compute, at least asymptotically. So basically every two rows are essentially independent. There's n choose 2 rows. And when I fix one row, the probability that the other row is the same is about 2 to the n. So it is 1 plus little 1 times, might as well write the correct thing, times 2 to the minus n. So n choose 2 rows times 2 to the minus n. There's a factor of 2 missing just because when you fix one, it actually fixes the sign of the other. And so it's a very natural guess that, and if you play around with it, that this actually might be the correct asymptotic for this. Right, so if you start to play around with it, okay, what if I create 4 rows or 3 rows that somehow have some sort of linear relation in a similar way, you start to see that this probability drops off a lot more, and you might guess that this is really the right answer. So, sort of, let's just say, conjecture, which is, let's say, folklore, probably some people have written it down specifically, that the singularity probability of this matrix is really equal to this probability 2 rows or 2 columns is equal. Okay. So I'm going to come back to this question in a second, but let me just sort of step back for a second and try to say something a little bit, more general about what's sort of going on. What do we know about symmetric random matrices, about their eigenvalues, and let's try to situate this result a little bit, or this question at this point. So let me just first by saying Wigner's semicircular. So this is not too recent, proved in the 1950s by Wigner. And what did he show? He said, okay, let's look at this random symmetric matrix. Okay, so this is also done in more generality, but I really don't care about generality. This sort of specific case sort of captures basically everything. Also here, essentially. Okay, so I have this random matrix. It's a random symmetric matrix, so I have a bunch of eigenvalues that are on the real line, which I have conveniently drawn. And now, as I send into infinity and rescale this picture correctly, so it turns out that this maximum eigenvalue is going to be about 2 plus little o1 times root n, and symmetrically over here, so this is minus 2 plus little o1 root n. All my eigenvalues will live in this range, so it makes sense to rescale by root n, and look and ask what sort of shape does this distribution make in the limit. And what Wigner proved in ancient times, that this distribution tends to a semicircle. So if I rescale by root n, the distribution, or the density of eigenvalues looks like this. By which I mean, if I look at the number of eigenvalues between, so let's fix some alpha and beta. If I look at the number of eigenvalues between alpha times root n and smaller than beta times root n, the proportion of eigenvalues that satisfy that is just the integral here. So this result tells us a very nice sort of, gives a very nice what's happening. Sorry, I should also say this is like improbability. So a typical sample satisfies, of course. So this gives us a very nice picture of what this sort of super zoomed out picture of all the eigenvalues, what's happening. If I look at on the scale of all the eigenvalues. But what's interesting is more recent work has shown that actually this picture is surprisingly accurate. So this is sort of like the super-macroscopic scale. There's also this work on the so-called local eigenvalue statistics.
Sorry, I don't understand. What does your picture represent? What's the first line? The eigenvalue, the spectrum of what?
Sorry?
On the left-hand side, you have the line, R, and...
sorry, so these are just my evals of the matrix Mn, which is a random matrix. So I sample the random matrix that has n eigenvalues. They're just some random points. What does that distribution of points typically look like? So you can make this formal by just like imagining, okay, I have a point mass on each eigenvalue here. This defines the empirical distribution. What does the empirical distribution tend to? It tends to this deterministic thing in probability. Okay, so there's also this business with local eigenvalue statistics. Which sort of says that this picture, I mean, it's a sort of a long project by sort of many papers, including Tao Fu, Erdős, Laszlo Erdős, Schlein, and Yao, and many co-authors here. But basically, one of the sort of key things this is saying is that, okay, let's say I want to zoom in on a specific eigenvalue. Say the ith eigenvalue in the ordering. So I'm going to order my evals. Of my matrix, and I'm going to focus it on some specific eigenvalue here. That's supposed to be I. It turns out that the location of this eigenvalue is really specified to pretty good accuracy by this original estimate of Big N. So one of the sort of consequences, very sort of nice consequences of these sorts of results, says that for such matrices, we have that the ith eigenvalue is equal to, okay, I'm just going to put this scale term here, which comes from that rescaling picture, times some number here, which I'll explain, up to some, scale. Okay, so what is this confusing thing that I haven't explained? This is what you would guess, where you'd guess the eigenvalue is if you only had access to this picture. So in particular, I would just, I just want to invert this distribution, sort of solve for where I over n proportional of my mass is, and that would give me a guess where that eigenvalue lives based on this picture. That's a number, that's just what I'm saying. Oops. So these local eigenvalue statistics actually say that this holds with high probability. So that the ith eigenvalue is actually sort of locally, and even sort of on this scale, which is roughly the spacing between the eigenvalues. Right? So I have n eigenvalues between 2 minus root n and 2 root n. So the typical spacing is like 1 over root n. And this is really identifying where each guy lives up to things that are happening on this typical spacing with high probability.
This is inside, no?
Sorry?
Is this even true for I equals to 1?
Right. Yes, this is also true. So it's actually done separately. So there is a distinction between bulk and edge eigenvalues.
Is this compatible with the Tracy-Widom thing?
With which?
Tracy-Widom? Which?
Right. So Tracy-Widom is going to basically be giving you the deviations on what happens here. This is just sort of the typical behavior. Right. So maybe the error term is different on the boundary. I see. Okay. So yeah, let's maybe stick to the bulk for today, which is where I'm going to spend most of my time. And epsilon. Yeah. Although you can actually push this even further. All right. Okay, so good. So, but what we don't actually understand from this kind of picture is what now starts to connect with this kind of question about singularity probability. We're actually interested not what happens on the scale of the typical spacing, but what's happened on even smaller scales, right? So this is sort of a very sort of small. I'm interested in pinning down the probability eigenvalues equal to a particular value. Or similarly, we could be interested in what's given some small interval, much smaller than typical spacing, what's the probability I have an eigenvalue in there? Or similarly, and this connects to sort of an interesting property of the spectrum, is that the eigenvalues sort of like to repulse each other. So they're not like, so you might guess that up to satisfying this distribution, you basically just look like a Poisson point process. Okay, maybe something funny happening at the edge here, but even let's say in the bulk, you might see you just look like some sort of Poisson point process with a typical density. In other words, you're sort of like as random as possible given that picture. But interestingly, this is not the case. And if I fix one eigenvalue to be here and push another eigenvalue to be close to it, sort of the probability that this occurs decays much more quickly than, or conjecturally decays much more quickly than Poisson. In fact, there's a particular heuristic. So we are interested in sort of, I'm going to call here microscopic. So that basically this includes singularity, the eigenvalue spacing, so this is sort of repulsion. Or crowding spectrum. Interestingly, even questions like if you just want to know like the smallest gap between the eigenvalues, it doesn't really fall under this framework because you expect the smallest gap to be much smaller than the typical gap. So this is not attacked by this. So this is about what is, even with high probability, the smallest gap. And this is the sort of question, and I'll say something about our results and this kind of thing, that we can sort of access once we sort of can understand first this sort of more basic question even of what's happening with the singularity problem. Okay. So any questions at this point, actually? Okay, so I just wanted to mention also this problem of understanding singularity has also been studied quite a bit in the IID case. So there's also a natural analog. So for us, we're very much interested in what's happening in the Hermitian case, or the just symmetric case, which brings us to understand something like this, which has been reasonably well understood in the just IID case. So let Bn, which I'll just say one word. So I say a few sentences about what happens for IID random matrices, and then we forget about it completely. Be a matrix drawn from, so all matrices, not necessarily symmetric, all n by n in minus 1, 1. And we can ask the same singularity question here. So again, the answer is sort of conjectured to be roughly the same kind of thing. But because we don't have this symmetry, which really adds quite a bit of extra constraints, there's been sort of more progress on this question. So this sort of questions goes back to Komlosh in the 60s. But sort of a big breakthrough was made by Kahn, Komlosh, and Sahasrabudhe. Showing that this singularity probability in this case is exponentially small. Also improved a bit by Tao and Fu, for gain, Fu and Wood. Until we have this very satisfying and a beautiful theorem of Komarov, just from say 5 years ago now, who really showed that in this IID case, we can sort of pin down the singularity reasonably well. We don't have anything as strong as like this. That's something certainly towards that. So this is equal to 2 to the minus n, so the right answer up to some sub-exponential factors. There's really like some really beautiful ideas in all of these works, but certainly getting it down to the sharp result. Okay, so is that counted? So let me just say very briefly sort of the history of what's known about this singularity probability in the back to the symmetric case. I'll tell you what we can say about it in some of these other kinds of problems here. So actually, so it's interesting that it wasn't known until basically the 2000s that this, despite being a genuine conjecture, that this singularity probability even tends to 0, right? So it seems obvious that if you take a random matrix with any sort of not reasonable not silly distribution, you should have that this probability tends to 0. So I'll just call this probability star. And this wasn't shown until the work of, so this tends to 0 was shown by, oops, sorry, Costello, Tao, and Wu in the 2000s. Then there was sort of, this was actually, they proved like a sort of polynomial rate, and then it was sort of slowly improved over a while. And I'll sort of write some results, and sort of a point will actually come from this. So it was improved by Wynne to sort of something super polynomial, and by Version into something stretch polynomial type. And there were some improvements on this constant until the work of Campos, Matos, Morris, Morrison. These are actually, this is Marcelo Campos, my co-author. This is actually Rob Morris. I'm also a co-author in other things. They pushed it all the way to here, and okay, and we actually managed to improve this a tiny bit more. This is sort of not the point, but this is CJ MS, and also independently Ashwin Saw and Mehtab Sani. Sorry, also with Jade to this. Okay, so there's sort of something kind of interesting happening with these results, and it sort of seems almost like they're converging to this. This sequence is converging to this exponent of root and log n. Sort of smaller and smaller improvements. And interestingly, this, as pointed out by these guys, is not a coincidence. And there's actually some really interesting barrier that occurs precisely at this point. So in all of these proofs, so here comes my matrix. Okay, so I have this symmetry here, which is causing headaches for really trying to get into understand these small probability events. And what they observed is all of these papers, I mean, including this one here, these papers here, for the really hard part of the proof, they're sort of just using the top half of the matrix, the independence of the top half of the matrix. Oh, of course, you can't just throw away the rest, it's important, but for the sort of really hard part of the proof, they're just using the top IID part of the matrix here, which is nice and independent. And they sort of showed that if you only restrict yourself to these sorts of arguments, you won't improve it beyond this point. Okay, so CMMM. So there's a barrier at this square root and log n exponent. And I don't want to say exactly what they're saying, but intuitively you sort of have to reuse the randomness of the matrix. You have to somehow get into these more complicated dependencies in order to get beyond this bound. And we really do want to get quite a bit beyond this bound. We want to prove something like exponential. Okay, so that brings us to the first result that I'd like to discuss today. So this is Campos, Jensen, Michelin, and myself that we proved a few years ago, where we showed that indeed the singularity probability is exponentially small. For some so there has to be some kind of new idea here, really, to confront these sort of previously scary dependencies that we had, which I'd like to say something about in a second. So this has to have some sort of needs new idea. And with this result, we're also really able to sort of attack some of these other, so sort of not completely finished with this business, so I won't say everything sort of formally. We can sort of really attack these other sorts of problems that are happening in these exponentially small scales. So opens up these other problems over on this board on microscopic scales. Even really exponentially small scales. Well, we'll see an example. Of course, as you could probably guess from the way I stated it, like our constant here is not sharp. We really hope that 2 to the minus n is correct, but at the moment we're really genuinely a long way from that. I think if you push like hell on our results, maybe you could get it down sort of up to like a square root to the 2 to the minus n. there still seems to getting this 2 to the minus n is really requires some further nuance. Okay, so I said also that it kind of opens up these. Well, what can we do with saying something about this? Let me state a first result in this direction. So I'll just state the result, and then I'll sort of say something about why this is sort of related to this business over here. So same situation. I have mn in the matrix, and now let's say I have some epsilon, and I'm interested in the probability that the least singular value is smaller than epsilon times epsilon over root n. So. So this is the probability I'm interested in. And we show essentially the sharp result here up to just the values of this constant. So for C bigger than 0. Okay, so let me just define some terms here. By the sigma min, of course, is just the of an n by n matrix. Is just the minimum push that it gives a point on the unit sphere. Which of course is also just the minimum distance from an eigenvalue to 0. These are the eigenvalues of my matrix A. And if you think about it for a second, this is the natural scale. This 1 over root n is the natural scale for this singular value to be living on. Right? Because I have n points. And the singular values are going to be living between 0 and, okay, we even saw the constant 2 root n. So we expect, just using the sort of a standard heuristic, that the closest root is going to be here on scale like 1 over root n. They're sort of all roughly uniformly spaced. And so what I've been looking at, I'm looking at the deviation from this, the extreme deviations from this expected place, and obtaining this sharp behavior. So also let me notice here that epsilon here and n, there's no limit anywhere happening. So if epsilon I could choose to be exponentially small, and this is still a valid result. So it's really saying something to us about what's happening even at these very exponentially small scales. So, okay. Okay, so, and you might think, okay, so I don't really care about the closest eigenvalue to 0, but this is also telling us, so there's a sort of a more general version of this result I can apply to the matrix Mn minus some Ti, assuming that I is sort of bounded away from the edge. Right, so now I've shifted all my eigenvalues, and if I look at the least singular value of this matrix, I'm precisely saying something about the singular values in a small neighborhood around this value of T. So this is saying something about the clustering of the spectrum in particular, around a particular value. Then before we move on, let me just mention one more kind of interesting aspect here. And it also gives us a sense that this problem is sort of, well, made available by this singularity result, is actually something kind of different. Because we have these two sort of terms that are really reflecting two different kinds of behaviors. So if my epsilon is kind of like moderately small, I mean, in fact, it can even be exponentially small, but even just say it's just like of some intermediate value, whatever, 2 to the minus root n or something. This is the dominant term. And this really is coming from a sort of behavior which says that, like, what's happening here is the least singular value is being dominated. This probability is dominated by just some direction, which will look sort of random-like on the sphere. I'm thinking of this expression here, that the matrix is not hitting hard enough. So I have this kind of nice sort of Gaussian-style anti-concentration. But when I push epsilon down far enough, say below some exponential amount, this term is dominating. So what's happening here is the most likely thing to happen is to have a very small singular value, is for your matrix just to be singular. And this sort of comes not from sort of a random direction, but from a very structured event, at least conjecturally, is we think like 2 rows or 2 columns are the same. So this kind of interesting situation. This is sort of being dominated by like a random point on the sphere contributing, and this is sort of a sort of collapse event that we see here. So this is kind of taken care of by our old ideas, and we need some new ideas to get this kind of behavior. Good. So I want to say something about how one sort of takes these problems apart and thinks about them. But let me just mention also that these ideas also allow us to prove basically the sharp bounds for these eigenvalue spacing, and like do things like determine the smallest gap, the distribution of the smallest gap of the eigenvalue. In fact, that work is forthcoming with not with this group, but with Ashwin Saw and Matos. Okay. So maybe let's just start. So that's all I want to say about this. And for the rest of the talk, I just want to give you some sort of flavor of how we sort of take apart this problem here, and what kind of, some sort of feeling for the ideas that go into it. Actually, maybe I'll just do that there. Okay, so let's try to understand this event. So the probability that the determinant, so I'll sort of say some naive things, and then we'll kind of slowly get into the juice of what's going on. So the determinant, this thing being 0, of course, is the same as the event that there exists some vector on the unisphere such that mv is equal to 0. So what we kind of want to do is try to understand sort of all points on the unit sphere and sort of how likely they are, or how much they contribute to this singularity event. What's interesting here, which is really different from the ±1 case, like, so if I had, say, like a suitable Gaussian matrix here, everything would just be sort of invariant and all the points look the same, and actually it's quite easy to calculate. I mean, so that's a continuous distribution, so this particular problem is not, just will have probability 0. But this sort of symmetry allows us to sort of compute eigenvalue statistics, whereas here we actually don't have symmetry. And in fact, the exact opposite is a huge range of different kinds of behaviors that we see at different points of the sphere. So, so let's try to understand. Okay, how this probability, we have m and v. I guess I'm not writing n anymore. Looks for a fixed v. for different v's. And here we kind of run into some sort of an interesting kind of Littlewood-Offord type situation. So I'll give some examples. So what if v is equal to a super simple vector, something like this. Okay. I guess I didn't normalize it. But now this event, that mv is equal to 0, is exactly the event that the first two columns are identical. So, in other words, I can easily calculate this probability. This is basically 2 to the minus n, or whatever. Maybe the factor 2. Doesn't really matter. Okay. What about the situation when v is equal to the all ones vector? Again, a very sort of structured looking vector. What do we expect this quantity to be? So here we have that m of the all ones vector. Okay, so it's already this is not completely trivial to compute, what this looks like. But roughly speaking, each row looks like a random walk, and I have to get 0 on that, so it's the probability that a random walk returns to 0, which is 1 over root n. It's actually constant over root n. And I have sort of n rows that are not independent, but they're kind of independent enough that we should expect something like this. Okay, we're just being sort of heuristic. So already between these two silly examples, I see like a huge range in the probability. Okay, so let's do one more example, which will be a bit of a different flavor here. Say I take now sort of a random vector on the unit sphere. Okay, so this is not exactly a well-posed question, or not an interesting question, because if I just take a random vector, there'll actually be no relations between it, so I can't have 0 at all. The right question here is to also introduce some parameter epsilon and consider the probability that mv is smaller than some epsilon beta. And here my epsilon I'm imagining is potentially as small as some exponentially small guy. Okay, so let's try to think about what this kind of probability is. And again, if I look at the contribution from a single row here, so v is a very random-like vector, and I'm taking an inner product with a sequence of plus ones and minus ones. Right, so a particular row looks like this. So this is sort of vi times some random epsilons here. Now, if these are very unstructured, we expect this guy, again, this is just heuristic, to look like, okay, have a central limit theorem, absolutely. But not only that, but obey the central limit theorem, even down to very small scales, potentially as small as this. So when I take a slice here of size epsilon, I expect this to be roughly approximated by a Gaussian, and therefore this is like constant times epsilon, just for one row to be sort of smaller than epsilon. To get this to get really the norm, for this to happen to all rows, you expect this to, so expect something like raised to n. Again, this is very heuristic. We sort of thinking that all the rows have no particular conspiracy with each other relative to v, this vector vi, so they should still behave independently. Okay. So here we see yet another type of behavior that can be even like, so epsilon can be like exponentially small, so this could be even like e to the minus n squared. Right, so we have, and really you can have any kind of behavior in between. So there's all these kinds of different vectors that we need to sort. So I just want to say sort of the structure of the result that we proved to understand this kind of probability. And basically what we want to do is show that if we look at all the vectors, so fix some scale epsilon, and intuitively, it's not quite a sum, but we're imagining we're sort of looking at the contribution to the singularity probability over all these different kinds of vectors. Okay, so fix a scale epsilon. Now, naturally, what I like to do is sort of see how much, how many, or like what's the measure or total contribution of all of these kind of vectors on the sphere to the singularity probability. And what I want to say is that that measure is small enough that it doesn't overwhelm and beat the thing that we think is the main term, which is the just coming from two rows, two columns are the same. Okay, sorry, that was a mouthful. I'll write down something that will be quite confusing, but I'll say a few words that hopefully we can understand. Okay, so here's like a key step. Is the following here. So let epsilon, so I want to fix some epsilon, possibly a very small scale. And I really need all these scales all the way down to exponential. And also fix some large constant L. So this is sort of some large constant. Okay. So here we go. So first what I'm going to do is draw a random vector on the unit sphere. So I'm going to measure the contribution from all these vectors. Okay. And now I'm going to look at the probability that I'll write it and then talk later. It's too early. I want this to be a gross L to the minus, say 2. Okay. So what am I doing? I'm interested in this probability. So this is a probability in the matrix M. And I'm asking, what's the probability that a random vector V, when I look at its concentration at scale epsilon, is much, much larger. So L is much, much larger than some constant than the random heuristic. So this is some fixed C, and now I'm choosing some large C. So what's the probability that this concentration is much larger than random? Okay, so what I'd like to say is this is an atypical event. And this is exactly what this is. This is sort of a concentration inequality, saying that if the probability of having this kind of concentration is very, very unlikely. Okay, and there's some particular relationship between, there's a reason there's a 2 here, but it doesn't matter so much for us at this level. So basically what this is, in a picture, is we're looking at the measure of points for which this concentration is large. And we can say that it's small, which makes sense because that's sort of contributing to the singularity event, and we're saying that these vectors at this scale are sort of staying out of the way of the singularity. Okay, so
This is for every n?
yeah, for every n, exactly. Yeah, so everything is sort of completely quantitative here. There's like basically no limit happening here. You just need to be careful. So the only kind of limitation in these results is something like this. If you choose your epsilon to be smaller than exponential, then you kind of run into problems because the probability, like there's only 2 to the n choices for a single row, for example. So you kind of just hit the level of discreteness. And here we're basically saying you can almost get to the level of discreteness. Okay, so this is really at the heart of the paper, this result. And I don't really want to say anything more about this, specifically this concentration result, which is really a key technical step. Well, I mean, a key step. But let me just say, one sort of tool that we developed to sort of, that comes in very handy in thinking about this kind of thing. So, so this is sort of some sort of decoupling inequality that allows us to prove sort of the negative correlation of two events. So by negative correlation of two events, I just mean we have sort of one side of the independence. And really, I'm not even going to get something as good as that. I'm going to have sort of all kinds of constants flying around, but we can sort of pull apart some scary events and deal with them separately. Okay, so let me just state this result as follows. Okay, so here's the setup. You're going to give me a point V on the sphere in n dimensions. And you're also going to give me part of a basis. So a bunch of actually orthogonal vectors. And you can actually give me quite a few of them. So k just needs to be bounded away by some specific constant times the space. So like constant proportion of an orthogonal basis. Okay. And we're going to draw this x from -1, 1, just uniformly at random. Okay, so here comes the two events that I'm interested in. Okay, so also I'll just say, like, as over here, epsilon is going to be some constraint which I imagine to be very, very small. And beta is going to be some sort of just like smallish, so just some small fixed number. So small but fixed. Okay. And now I'm going to be interested in the following two events. So x, v. So here's the random walk with step sizes in v. And I'm going to be interested in the probability that this is smaller than epsilon. So here I'm looking at these very, very small slice of a random walk. Okay. And at the same time, I'm interested in how this same random walk is moving these points around as well. So in particular, I'm interested in, I'm interested in the probability that from the perspective of these guys, this is just smaller, sort of slightly smaller than we expect. Sorry, just to be clear, so this guy here, his typical value will be like 1. So the expected value of this is like 1, the expected value of this is like 1. So this represents sort of, if I just isolate one of these events, this sort of holds a sort of constant probability. There's a beta probability. But now I want to look at this for all I in my basis, and at the same time I want to look at this scary event. So our main new decoupling inequality basically allows us to split these two events. So the probability of these two things happening together is approximately, in a way that I won't stay here. Oh, I see. Is that, I don't know, do I give 5 minutes or?
Yeah, you have 5 minutes.
5 minutes, okay, so. Okay, well, I'll take, I'll take 3, so. I can just write. So then what we can prove is that if I look at these two events together, and this is sort of a big, confusing mess of random walks for all I, we can approximately split them and look at them separately times probability. So this is for all I. And I can do this unless something, so we saw the situation like there's these vectors, like I had these vectors that were like the all ones vectors, or like 1 minus 1, they have this sort of particular structure. And that sort of throws a bit of a wrench into this business. But what we can say is we have it, or we can identify that V is structured. Yeah, like in particular, there'll be like a large value Fourier transform, or something that's actually quite easy to work with in this context. So we can easily deal with this. We can split the events. This is something that we can understand. There's techniques to understand. This is something we can understand. So this really allows us to deal with these sort of complicated events. Okay, so I think I'll stop there. Thank you very much.
Thank you for this interesting talk. Any questions? Yes?
So probably my intuition is wrong here, but I would expect that the probability that there are, I mean, regarding the conjecture in the beginning, the probability that there are linearly dependent rows would have been much larger than the probability that there are two which are equal to each other at cosine. So at least in the n square, shouldn't we expect something bigger?
Sorry, that there's two linearly dependent rows?
No, or more.
Or just some confusion? So this is exactly, I guess this is exactly in the meat of what's happening here.
Okay.
So basically this vector V is sort of encoding, we're trying to understand all sort of possible linear relations that could occur.
Yeah, and aren't there many...
Yeah, to be honest, it's not completely clear that somehow there's some very, like, typically it's like a random vector that dominates. Yeah, so I think that's not a wrong intuition to have.
Okay.
It's not, just sort of, I fed you a particular intuition for the purpose of the story, but it's also possible that the high entropy sort of dominates.
So do you still expect that the n square is the right prefactor, or?
Sorry?
The n square, you had an n square in the beginning coming from the lower bound. I mean, n squared times 2 to the n, 2 to the minus n.
Yeah, right.
Do you still expect that this is the right?
I think for me, I still think the other end is still probably the sharp one, but it's not. You have to really get into it to understand. Yeah, thank you.
In the non-symmetric case, is there a similar conjecture for within the middle row? Is it 2n squared or?
Yeah, exactly. It's the conjecture is the same, and
The same or twice? Exactly the same?
right. So because then there's rows and columns, so then I think it's a factor of 2. No, I think it's actually the same, because it's just weird because the symmetric version, like once you fix one column, then it fixes the sign of the next one just by the one. But I guess so maybe it's exactly the same. Yeah. But I mean, I guess more generally, the conjecture is for these models, you expect that the 2 rows or 2 columns equal up to sign dominates. Is really the. So interestingly, this is proved for the non-symmetric case. There's kind of a very beautiful trick also due to Komarov that allows you to deal when your distribution is, say, non-uniform or something like this. But in this case, it's very much open, even for IAD case, which should be considerably easier, still very hard.
I guess the intuition is that if you have some bounds on the on the entries of the matrix, but you still consider a linear matrix. Your model is the worst one for the singularity. Is it something that is understood, or is it at least true that you have?
Yeah, so I mean, I guess you need to add maybe one more condition, because if you have a very biased distribution, so say it's, then the most likely thing is to say it's 1 with probability p and 0 with probability 1 minus p, then the most likely thing is just to have all zeros. But,
say centered.
yeah, so centered.
Various 1 and fourth moments bounded.
Yeah, it seems, yeah, right, something like that. It seems reasonable that this is the extremal probability.
Are your methods specific to this kind of dependency, or could you deal with some more general setup where there is some other kind of dependency between the entries?
Yeah, it's definitely more general. Yeah, I haven't really thought about like what the right class this kind of model would apply to. Yeah, so it's certainly more general than. In a way, it's reasonably flexible, but I don't quite know the right question. Yeah.
It was an open-ended question.
Yeah.
Other questions or comments? Yes.
Is it possible to prove how does the probability of singularity compare with the IAD case? Like, you know, in the limit, the conjecture will be the same, but which one is bigger, for example?
I don't know a way of directly comparing these two models. There are some nice tricks to comparing actually these sort of like Littlewood offered probabilities, but yeah, I don't know any trick other than to sort of try to understand each one independently. It would be really cool if there was such a method. There are, sorry, if you're looking at, it might be good to just preface that, that there are ways of making comparisons between matrix models for these sort of, at much larger scale. So like these are actually a lot of these ideas of Schleining now is like they're interested in one confusing matrix model, and you want to compare it to a matrix model that you understand, like for like something like a Gaussian or a GUE, and you could sort of flow one model to the next. But I have no idea how to make it work for this kind of problem.
More questions? No, then let's thank Julian again.